Good afternoon, everyone. And first, I would like, of course, to thank the organizing committee for giving me the opportunity to take you with me to my journey to unravel the sun's chemical past. So I'm a PhD student at IPAG in France under the supervision of Tuccia Ceccarelli and Anna Lopez Sepulcre. So, yes. Here is a nice artist view of our solar system, and in astrochemistry there are still some questions that we want to answer. So, for example, what happened to the first phases of the solar system? How did organic chemistry develop in the first phases, and how did it affect the appearance of life on Earth? And there is in particular, a question that I was trying to answer during my thesis, which was, what is the chemical past of our sun? So the sun's birth environment has long been dissipated, of course. So what we do is to look at other solar-like planetary systems that are forming. So here you have a side view of the Milky Way, and I put some of the star-forming regions that are the most studied. And so there are several chemical surveys that targeted those regions to understand, to try to see the chemical composition of solar mass protostars. So a first result of the study showed that there is a chemical diversity among solar mass protostars that don't share the same chemical composition. In fact, we can find two chemically distinct types of solar mass protostars. So on the left, you have hot corinos. These are dense, hot, and compact regions that are enriched in interstellar complex organic molecules. Those molecules are of particular interest because they are precursors for prebiotic molecules. And the envelope of those objects are usually deficient in carbon chains. The prototype is IRS 16293242 system, as you can see on the bottom. And on the other hand, we have warm carbon chain chemistry objects. So those objects have their inner region that is deficient in ICOMS, but in their envelope, they show a large enrichment in carbon chains, and especially in long ones. And the prototype is L1527. So we want to understand the ancient chemical nature of our sun. Was it hot corino, WCCC, a bit of both, or neither? So taking again the same picture as before, there are some of those objects that have been found in the star-forming regions I showed you before. The problem is that all of these star-forming regions are forming only low mass stars, and so they are not really representative of the sun's birth environment. Because we think our sun was born in a large stellar cluster with high mass star in its vicinity, as in the sketch that you can see here. So in order to find the ancient chemical nature of our sun, we need to target solar mass protostars that belong to that kind of regions. So during my thesis, I focused on the Orion molecular cloud, which is the closest high mass star forming regions. It's about a bit less than 400 parsecs away from Earth. And in particular, I looked at the OMC23 filament that you can see here. It is considered as the closest and best analog to the sun's birth environment because it is surrounded, as you can see, by several H2 regions. So we wonder, are there any hot corinos or WCCC in that region? So very recently, there are 3 hot corinos that have been detected, 2 intermediate mass protostars, MMS6 and OMC2 FIR3. And there is the solar mass protostars HOPS 108 in the FIR4 protocluster. And for now, there is no evidence of any warm carbon chain chemistry object. So part of my thesis was about characterizing the chemical composition of solar mass protostars in this filament. So it is the Orion ALMA New Generation Survey project. So we have ALMA observations at 1 millimeter and an angular resolution of 100 AU. And I targeted all of the protostars that are marked by blue circles. So first, we wondered how many hot corinos are there. So we targeted first methanol because it's the most common ICOMS found in hot corinos. So we detected methanol towards 5 of those objects. Here in orange color, you have the 1 millimeter continuum of the 5 sources. The white arrows represent the direction of the outflow when it is known. And I put in green contours the moment zero of one of the methanol transition. And you can see that the emission is quite nicely centered on the dust peak continuum. And because we detected several methanol transition, we could derive the physical conditions of the gas that emits this methanol. And we found that the gas, the region is dense, hot, and quite compact. So we detected 5 new hot corinos in the OMC2-3 filament. So we wanted to compare the detection rate of hot corinos in OMC2-3 filament with that in the Perseus molecular cloud. So this is a study of pitches, Perseus Alma Chemistry Survey. They did the same study in the Perseus. They had a sample of 50 solar mass protostars. And it is useful to compare the two regions because they are very different. One is more dense than the other, and the OMC2-3 is more illuminated. So in Perseus, they found that hot corinos are very likely abundant because they found for 56 of their source sample that show regions corresponding to hot corinos. And in OMC2-3 filament, so out of the 19 solar mass protostars and adding the previously detected hot corino, we have 31% of hot corinos detected. So we have a high statistical error because we have much less protostars, but overall, we can say that hot corinos seems to be scarcer in that kind of regions, and that pitches seems to be different than oranges. So what about CCC sources? So for that, we started by targeting CCH, which is commonly found in WCCC. So CCH has been detected towards all of the protostars, but here I show only 2 examples. So you have again the 1 millimeter continuum in orange scale, and the CCH emission is shown in green contours. So here it appears that CCH traces mostly the outflow cavity walls. And in a general way, CCH is tracing more extended protostellar envelope, so around 2000 AU. So the problem here is that with oranges, the largest scale that we can probe is 800 AU. So if those sources have a WCCC zone, it's most likely resolved. So for now, we cannot determine whether there are WCCC objects in OMC2-3. We would need less high angular resolution observations to probe a larger scale of the protostars envelope. What we can do is to look also at other carbon chains that are known to have a more compact emission in WCCC object. And I'm currently looking at the cyclic C3H2 to see if first, it's detected because it has not been detected towards either of the 50 source sample in pitches. So yeah, it needs to be continued. So if I can summarize quickly, we found hot corinos in a solar-like birth environment, but they don't seem to be prevailing. So is it the case in every other analog to the sun's birth environment, or is OMC2-3 special? And for now, because of observational bias, we don't have any WCCC sources. So of course, we need to increase the statistic because we have only one region. So we need to target other high mass star forming regions. So where are those high mass star forming regions? On the left, you have a plot taken from Red et al. 2019 showing basically the galaxy with the different arms. The sun is right there, and all the dots represent high mass star forming regions. And if we look at the distances of those regions, it's the table on the right. So here is just a sample of main star forming regions. Only 3 of them are less than 1 kiloparsec away from us. So it means that most of the high mass star forming regions are much further away. So we need to target those high mass star forming regions. Another thing that is interesting is that our sun is probably born closer to the galactic center and then moved away. So the chemical composition that we find today may not reflect that of the ISM 4.5 billion years ago. So when we target different high mass star forming regions at various distances, we can study solar mass protostars chemical composition in environments that have different metallicity. So the idea is to perform an unbiased chemical survey of solar mass protostars that are located in high mass star forming regions. So for that, what do we need? Of course, we need a high angular resolution, because as we saw, they are much further away than Orion region. And if we don't have enough resolution, what will happen is that we won't be able to probe the protostars themselves. There will be the line emission will be mixed with that of their environment. This is, for example, what we saw by observing Orion with single dish observation. So we studied CCH and methanol with single dish telescopes. And we found that the molecular line emission was contaminated very likely by the photodissociation regions of the regions due to the nearby H2 regions. So we need a high angular resolution if you want to avoid this configuration. Of course, we need also large instantaneous bandwidth to do multi-frequency surveys, because we want to be able to target at the same time ICOMs and carbon chains. So we thought that which observatory would be the best instrument. We think that the NOEMA interferometer will be very useful for that kind of study, in particular because of the next upcoming improvements. So there will be a larger instantaneous bandwidth with the upcoming spectral scan, which will enable simultaneous dual band observations. Also, the baseline will be extended, so we will have also an improvement in the angular resolution. Also, we wanted to share the idea of developing NOEMA to lower frequencies. Of course, we cannot go at higher frequencies, in particular for ICOMs, because we will encounter some optical depth issue, and I guess Marta will talk to you more about that on Thursday. And for WCC object, the long carbon chains have their transition mainly at low frequencies, so around 40, 50 gigahertz. So it would be nice to go in that direction. And I'm already done.
So, are there some questions?
Maybe a very basic one. What do you mean by warm environments in terms of temperature?
So warm for the warm carbon chain chemistry. So these objects, in the envelope, the temperature is more than 25 Kelvin, 30 Kelvin, because there is this methane that will be able to dissolve and produce long carbon chains in the gas phase.
And in terms of carbon chains, so I saw acetylene, also C2H. What are the other ones?
So in the prototype, there are there is a CCHS, which is the most common. C4H, CC3H2. There is also longer carbon chains, C6H, C7H also that have been detected. It's that kind of and C I don't remember. Maybe. Yes, cyanopolyenes too. Yes, thanks. Okay. C4H2.
What do you need to get to lower frequencies with NOEMA? You need new correlator, new detectors?
So I am not expert of how it works really, but I think it would be new correlator. I'm not sure, or I don't know. Maybe someone knows better than that.
I can say we probably need new receivers, so we need new front-end detectors. Correlators would be okay, I guess. But then the question, if we go to lower frequencies, aren't there other facilities that are better suited for that? 40 GHz is the VLA, EVLA, and GVLA, SKA. I don't know what's the upper range.
That's ambiguous because our antenna, where the NOEMA antenna will have a much better efficiency. But isn't it 40, 50 gigahertz would be the equivalent of the equivalent of the band 2+3 of ALMA?
That's the band 1 for ALMA then.
That's the band 1. Okay. And the band 1 has not been produced for ALMA.
It is currently being produced. Yes,
it's produced.
Ongoing.
So that would be, you mean that would be a different receiver? It's not possible to do 3 mm and 40 gigahertz at the same time.
You mean a dual band in parallel?
No. I mean in the same junctions, in the same mixers.
That's too much bandwidth.
That's too much bandwidth.
So Benoit, you had a question for Mathilde?
Yeah, I had a question.
Yeah,
so it was about the slide, your first slide about the difference between warm carbon chain sources and hot corinos. Do you think that it's really intrinsic difference in the chemical composition of the envelope, or just the difference in the structure of the source? Because what you showed is that, at least for your observation, but this is also what we see in other sources with ALMA, is that the carbon chains are tracing mostly the cavity. So perhaps some sources are rich in warm carbon chains only because of the geometry of the cavity. Say, if you have a large cavity, then it's very much irradiated, releasing perhaps methane or destroying carbon grains, and so triggering this warm carbon chain chemistry.
Yeah, so the difference between, so what could produce a WCCC object? So we think it's come from the ice composition that is settled at the pre-Stelakov stage. So it would be a ice mantle that is enriched in methane. And so it would be a different process. So I guess that there are carbon chains tracing outflow cavities in every protostars. Either it's a warm carbon WCCC object or not. But there are some objects that produce even more carbon chains with more compact emission. So it can trace also the outflow cavities, but we will see also a kind of emission centered really on the protostars and not only tracing the cavity walls. Did I answer your question? Or?
Yeah, and about that, any perspective with James Webb to detect these ice features and see, because you would then expect to have a strong differentiation between different clumps, different cores, I guess, in your ice.
So I guess with the GWST, we will be able to see the composition of the ice, basically. So if the difference between hot corinos and WCCC comes really from the ice composition, we will see a different we will be able to see it with the GWST, I guess.
Okay, thank you very much.
Thank you.
Okay, thank you. So